Hi everyone. I will quickly summarize what we are going to learn on this for this particular demo actually. So on the adversarial attacks and machine learning systems, right? Today we are going to see a demo on two particular subjects. One is model evasion and another one is model poisoning. We are not going to see a demo on for example, we are not going to study other attacks like model extraction or model inversion, for example, or attacks on LLM specifically. So these attacks are specifically the two subjects that we are going to concentrate on are model evasion and model poisoning. So this is specifically targeting classification based ML models. I would say like predictive AI actually, not like LLMs or other which are like text based and other things, right? Which are like generative AI. So these attacks are specifically concentrated on classification based models actually. So initially we will start up with the basics, and then for the first demo we will be seeing how we can attack an image based classification model actually. Say we in self-driving cars and all, there will be like autonomous models which the duty of which is to interpret the objects on the road or the different images actually. So we will take an image of a actual stop sign, and we will perform the attack on the stop sign, and the machine learning model, which is like a ResNet model, pre-trained nested model, we are making sure it misclassifies a stop sign as a green signal. Basically misinterprets a stop sign as a green signal, which will be which in case of autonomous cars or self-driving cars, right, would have many implications. For the second demo, what we are going to do, right, we are going to take a SQL injection data set actually. So we have a data set which is based on there are two class labels. One is we have benign SQL queries, and another one is we have malicious SQL queries to exploit SQL injection. And we are going to train a model on this benign as well as malicious SQL queries. So this machine learning model will be able to detect what is a normal SQL query and what is a malicious SQL query used to exploit SQL injection. And once we have trained that model on the SQL, basically this is an SQL injection detection model. Once we have trained that model, we are going to attack that model. So we are training a model and we are going to attack that model using a generative adversarial network called as GAN actually. That is for the second demo. And the third demo is on model poisoning. It will show the impact, say for example, if we have access to some DevOps platforms, or if we gain access to some DevOps pipeline actually, and if we have access to the model code that is used to train the model itself, what are the implications, what are the things we can do, that we will see on the model poisoning actually. Okay, just a very basic explanation about machine learning models actually. Say for example, if you are trying to teach a child on how to identify different fruits, like we are trying to teach a child, we show the child different images of apple, carrot, right? So over a period of time, the child will be able to identify the different patterns, such as the shape of the fruit or the size of the fruit or the color of the fruit, and the child will be able to identify and classify different fruits. In very simple, similar context, like what we do with machine learning models, right? We train the machine learning model on a vast amount of data. For example, I will give a quick example. Say for example, if you are training a model to classify malware, right? We take multiple, millions of malware samples, right? Multiple executables. We try to extract features from the malware. When I say features, each malicious executables or malware samples, right, would have some kind of a specific techniques, right? They will be using specific Windows APIs for evasion, or they will be using LOL beans for evasion. They will have certain strings, hard-coded strings embedded. They will have some metadata. So we'll extract all the features from these malicious executables, right? And once we have we have say for example thousands of malware samples. We have extracted these features from the malware samples, right? And we use these features to train a machine learning model. So the machine learning model, right, will try to understand the different patterns within the malicious executables. For example, the different malware, right, what specific techniques they are using, which APIs they are using. Are they supposed to use those APIs? For injecting into memory or copying shellcode to memory, or what are the hard-coded strings that they are using? What is the domains that they are trying to contact? So the machine learning model will try to understand all this context actually, try to extract all these features. It will try to understand and correlate all the information that is extracted from these malicious samples, right? So it learns on its own. once we have fed all the features, all the we would say like all the dimensions or all the features of a malicious executable to the machine learning model, right? It will try to interpret and try to correlate the data and then use that data to identify malware. So now we have trained that machine learning model on some known malicious executables. Say for example, millions of malicious executables. Now the model is ready to classify a particular executable is malware or not. So it uses that learning that it has undergone throughout the training phase to classify malware on real world unknown and unforeseen scenarios. Now like it has undergone the training, now we can deploy the model into production, and we are submitting a new executable, right? It could be malicious or it could not be malicious. Based on the training it has undergone, it will be able to classify whether the executable is a malware or not a malware. So that is the idea behind machine learning, like very simple explanation actually. Okay, to the training phase, right, there are like the different training methods actually. Just to quickly summarize, like this is not needed for this demo, but just to quickly summarize, right, like the supervised learning. So in order to train the model, right, I mentioned about data set. So the data set that we provide to that machine learning model, right, in supervised learning, we explicitly label it. Say for example, if you are training a model to classify images, right, we give it images and with an explicit label saying this is an image of we give it an image of a cat with an explicit label saying cat, or we give it an image of a dog with an explicit label called as dog. So in supervised learning, like we give the additional context information label for the machine learning model to learn on its own. Unsupervised learning is something different. Like say for example, in case of bank transaction, right, here in unsupervised learning there are no explicit labels. Like imagine in bank transactions, say for example, if a user is doing different bank transactions, most of the time like say for example, the user is based out of India, so most of the time the transaction is going to happen in IST hours, or like in the morning or the daytime IST hours. So we have the history of all the transactions made by the bank transactions made by the user. So we submit it to the model actually. So it will try to correlate and understand the relationship between all the transactions that the user has done. So now here we are not explicitly labeling anything as like this is a malicious transaction or this is a normal transaction. We are just giving all the transactions that the user has done to the machine learning model. So based on the timing, say for example, based on the IP address from the web from which the transaction was made, the time in which the transaction was made, and the location, like whether it is based out of India or any other country, based on these details, the machine learning model learns on its own actually. So there are different algorithms for this. Like one of the algorithms is like I would mention k-means clustering. There are different algorithms. So it will try to find the odd one out. So now we have all the set of transactions. So it will correlate all the transaction and it will try to find the hard one out. So if any malicious user or a hacker is like doing a malicious transaction that happens from some other country, right, like Sri Lanka for example, and it is happening at night time. Okay, so this is the odd one out. So it understands the relationship between the different bank transaction and it will find the odd one out and learns on its own. So that is the idea behind unsupervised learning. In reinforcement learning, a good example would be like, say for example, we are developing a machine learning model to play a game, for example chess, right? So we are developing a machine learning model to play a game, for example chess. So if the machine learning models makes some good moves, right, so that ultimately it wins. So in the process of playing the game, if the machine learning model makes some good moves, we give it some rewards, saying like this is a good move, right? And if the machine learning model does some mistakes or does some bad moves so that it loses the game, we give it a penalty, right? So if it makes some good moves, we give it a reward. If it makes some bad moves and it ultimately loses the game, we give it a penalty. So this feedback mechanism is there in reinforcement learning. So this is typically like another scenario would be like autonomous self-driving cars, right? So based on like we implement in a controlled environment, we have the autonomous machine learning model to do the self-driving, and we give it rewards based on how well it is driving, and if it violates a road sign, or if it causes an accident, right, we give it a penalty. So based on this rewards, penalties and feedback mechanism, this machine learning model learns on its own, and then we can and uses that learning to perform in real world environments like autonomous driving, or to play a game against a professional chess player in real world environment. Okay, so before we move to the demo, right, there are some basic concepts that we need to understand, like we can move to the actual demo. I will explain this with an example. Sorry. Okay, so say for example, if we are training a machine learning model to classify, like we are going to into the particular machine learning model, right? We are going to input multiple data, like what is the plot size, like whether it's a 2 BHK or 3 BHK, and whether it is near to the main road or far from the city. So we are going to input the data to the machine learning model, and the model's output should be like, it should classify based on the data it has received, right? It should classify whether the house is like luxurious house or a affordable house. So that is the idea behind training this machine learning model. So this is a machine learning model that will classify the house whether it's a luxurious house or a affordable house. So here these are the inputs that we are going to give. One is the plot size, whether the number of bedrooms, like 3 BHK, 4 BHK or anything, right? The number of bedrooms, and proximity to the city or the main road. Like these are the, so to determine the final price, right? So to determine the final price of the house, it has to receive all these inputs, like the plot size, the build-up area and all these things. So these are the typical inputs that it will receive. And these are the inputs that it has to give importance, like plot size, the number of bedrooms, the build-up area. These are the inputs it has to give much importance in order to determine the final output, whether final class level, which is affordable or luxury. So in order to convey or let the model understand that you have to give importance or priority to these three inputs in determining the final price, right? I repeat again. So we have to let the model know that you have to give importance to these three inputs in determining the final price. So how do we do in machine learning, like in machine learning field, right? So we tell it like we ask it to give importance using a concept called as weights, actually. So weights are nothing but like some kind of numerical numbers, actually. So this is to denote, say you give importance to the plot size or the number of bedrooms or the proximity, based on the proximity, like how close it is to the main road or how close it is to the city. So if you want the machine learning model to give importance to these particular inputs, we assign weights to it, actually, and based on the weights it will determine the final price. Weights are nothing but like you can imagine it as some numbers, but the idea behind using weights, right, is to inform the model you have to give priority to these inputs in determining the final price. That is done using weights, actually. So like nothing like some numerical numbers, actually. So bias, there is another concept. There are two concepts. One is the weights and the bias. Like bias. So like now the model, based on the inputs, right, the plot size, the number of bedrooms and proximity to the city, it has determined a price, right? It is determined a price, and now it will be able to classify whether the house is like a luxurious house or an affordable house, like for the middle class. But like say for example, in the final price that the model has determined, right, if you want to offset, like add plus 20, like say for example add plus 20 lakhs or offset or reduce 20 lakhs from the final price. Say it has determined a final price like 1.3 crore, right? So you have to add some 20 lakhs, or you want to reduce some 20 lakhs. You want to offset, like either add or negate some price, right? That is done through bias actually. So these are like weights and the bias are like underlying machine learning concepts actually. So weights we use it to let the model know that we have to give importance to the particular input, and bias is to offset the final price. Say for example, in case of this particular machine learning model, right? Say for example, if the house is within a gated community, you have to add, like generally they do, right? If the house is within a gated community, they will add some 5 lakhs more, right, to the final price. Or if the house comes with multiple amenities, right, they will add 2 lakh more, like the maintenance charges and other things and all they will add. So that is done through bias. Or if the house is an individual house, right, it doesn't have any amenities, then like the price based on the inputs, right, the final price is like, say for example, the price that the model has decided is 1.3 crore, but the house doesn't have any amenities, right, it is not within a gated community, then we can reduce some for 5 lakh or from the final price, right? We can reduce some 5 lakh or 10 lakh. That is done through bias. So combining weights and bias, the model takes decision like whether the house is affordable or a luxurious house. That is the idea behind weights and bias. Feel free to interrupt, like if you have any questions actually. Okay. So as I mentioned, the first underlying concept is like weights and biases actually, which will be used by the model to determine the final output actually. So this is a typical explanation of like a typical diagram of a neural network actually. Like I am not going into like the explanation of a neural network, but generally it resembles our neurons within our body, like the neural network, like it resembles the neuron within our body. Like say for example, how we touch a thing and perceive the information, and perceive the information, right? It will be transmitted from one neuron to another neuron, ultimately to the brain, right? Similarly, it is like it resembles the underlying concept behind neural network was to resemble a biological neural network, right? So just imagine this is a single neuron, like just imagine this is a single neuron, and these are multiple neurons, okay? These are the inputs I was talking about, that the number of bedrooms, the plot size, everything, right? So we are giving the plot size, the number of bedrooms, and the proximity to the city. So this we are giving as inputs, okay? And what the neuron does, right? It adds weights to it. Like we have to give importance to it, right? We have to give importance to this particular input in in determining the final output, right? So based on the inputs that we have given, it adds weights to it and gives the result actually. This particular neuron, it gives a result, okay? This is one step actually. This is called as forward propagation or like optimization, but we don't have to know about that. The second one, like here, like consider the same thing, but in case of a neural network, right, there will be multiple neurons. This is what a single neuron does, but in case of a neural network, there will be multiple neurons, right? There are multiple neurons, and the 3 inputs that I was talking about, right, the number of bedrooms, proximity to the city, and the plot size, right, will go to each neuron. All the inputs will go to each neuron actually, okay, and each will be determined whether the house is affordable or luxurious. This is what, like a very simple explanation of a neural network. This is what happens behind the scene, okay? So now we have the final output, but what if the final output is not the correct answer? What is the final output is like not the expected answer or not the correct answer? So machine learning models also make mistakes, right? So we use loss function, a kind of mathematical function called like there are multiple functions. One of the function is like cross entropy. We use a loss function to determine how wrong the output is actually. Like what mistake, whether the output is wrong or right? Well, what that we measure using a loss function called as loss function actually. So how wrong the model's output is from the baseline or the actual result. So say we have the final output, and we use the loss function to measure if the final model output is right or wrong. And if the loss is like big, right, ideally it should be small. In case of production environment and all, the loss function, the value of the loss function should be nil or like very small. If the loss function is big, right, ideally it will go back to again to the neurons, and it will reassign the weights actually. So now it has, like you mentioned, that we have the inputs and we are adding weights to it and in determining the output. So if that loss function is like big, loss function is nothing but imagine it's a number actually, right? Imagine it as a number like 340 or 450 like that. If the loss function, the value of the number is like very big, that means the model output are like not suitable for real world environment. The model is making mistakes, right? Not suitable for deploying into production. So that is determined using the loss function. And if the model loss function is quite big, we again go back to the neurons actually. We again go back to the beginning. This is called as back propagation actually. Again, here what happens, right? That the same process repeats, the same training process repeats. What the neurons, right? It reassigns the weights that to the inputs. It reassigns the weight. It changes the weights, and it gives another results. So this happens. This training phase happens and happens again until the loss function is reduced. As I said, right? Ideally, the loss function should be like very less. This training happens again and again. It reassigns the weights to the inputs again and again until the loss function is quite small, and also like the output output of the machine learning model is desirable, so that we can deploy it in production in actual real world environment. So this is the idea behind weights, biases, and loss function. And gradients is again a mathematical concept. It is used to determine how, say we are changing the inputs, right? Like we are changing the inputs, the weights associated with the inputs, right? How this change affects the loss function. How this change, whether with the change in the weights, the loss function is increasing or decreasing, right? In certain cases, even if we reassign the weights, the loss function might increase. The model still gives incorrect predictions and incorrect output. So to verify whether based on our inputs that we give, whether the loss function is increasing or increasing is determined using gradients actually. This will be helpful from an attacker point of view. This will be helpful because ideally the attacker want to change the input and deceive the model. So ideally from an attacker point of view, he wants to increase the loss function from an attacker point of view, right? So he will change the input. Like for example, if you are SQL injection, for example, if you try to bypass a WAF, right, like in normal pen testing, right, and all, if you try to bypass a WAF, so we make changes to the input and see if the WAF is blocking us or we are bypassing the WAF. Similar concepts only. So we make changes to the inputs and we query the gradients to understand if the model is making mistakes or not. Ideally, from an attacker point of view, the loss function should increase, but from a developer or a ML engineer point of view, he will train the model so that the loss function will decrease. And the gradient is an important concept, like this kind of a mathematical function, like that helps us to determine whether the loss function is increasing or decreasing based on the inputs that we have provided to the network. Concept like quick walkthrough on the hard labels, scores, soft labels, and decision boundary. Like we would have talked about that the machine learning model to classify house prices, right? Affordable versus luxury. So the hard label is the final answer of the model. The hard label is the final answer of the model, whether it's affordable or luxury. That is the hard label. In certain scenarios, we won't get the in certain scenarios, we get only numerical outputs from the model. These kind of numerical outputs from the model. This indicates a confidence, this kind of numerical values, right? 0.85 or 0.50 indicates the confidence that the model has in this particular output. So there are only two in this particular scenario. For this particular machine learning model, there are only two scenarios. It gives an output whether the house is affordable or luxurious. Okay. So there are two class labels, the red one and the blue one. Okay. So say after the training, after we have given the input, and it will make a final prediction. The model will make a final prediction in the form of a numerical outputs. So this is 0.85 and the other side it would be 0.15. This indicates the confidence that say for example luxurious, right? Yeah. This indicates the confidence that the model has, that based on the input, the model believes that this particular house belongs to a luxurious category, right? So this numerical value indicates a confidence that the model has that this particular input, like based on the input that has received, this particular house belongs to a luxurious category, right? So scores are just numerical outputs which indicates a confidence that the model has in a final, in a particular class label or a final output actually. When the scores, these confidence values are converted into probability, like percentage probability, that denotes the soft label. When we convert this into probability, we get the soft label. And decision boundary is like an imaginary line. This is an imaginary line, this doesn't exist. Like where, say for example, like if we cross this decision boundary, it will be affordable. If we come in this side of the decision boundary, it will be luxurious. So this is an imaginary line that separates the two class labels. From an attacker point of view, he wants to, like attacker would be like, he wants to stay around this decision boundary, so it looks normal to a human person, but the model misclassifies it actually. So from an attacker point of view, the attacker would use the decision boundary to cause misclassification, where like he will change the input. The change would be looking normal to from a human perspective, from the model perspective, right? It will misclassify it into another class label. That is the idea behind these values. Okay, coming to the first set of attacks, model evasion actually. So as I mentioned, like in case of an SQL injection attack, we try to bypass a valve. We make changes to the SQL queries, we encode it, we do some random stuff, inject comments, like we do make multiple changes in order to bypass a valve. Similarly, in case of machine learning model, we try to play with the input. We make subtle changes to the input and eventually deceive the model into giving incorrect results, or basically make it to misclassify an output, actually. And a particular example would be like in case of spam detection models, right? Say for example, we are sending mails and the model classifies this particular spam mails, like we are sending phishing mails, right? And the model classifies it as a spam or something like that. So we try to play with the we try changing the text URL patterns, we try to blend in with the normal, right? So we make subtle changes to the input. So from a user perspective, it doesn't look like a spam. It looks very normal. But the model misclassifies it as like actually it is a phishing mail, but the model misclassifies it as not a spam. So that is the idea behind model evasion actually. So like there are various implications actually. One of the research that was done here, like based on this particular paper, right? What they did, right? On the side of the roads, there will be like different street signs, right? Like stop sign or go fast, like speed limit or something like that. So what these researchers did, right? They stuck some posters on top of, there's some small posters or stickers on top of the stop signs actually. So there was a stop sign, and these are researchers, they stuck some small stickers or posters on top of it. But to the human eye, right, it will still look like a stop sign. They have not made many changes to the stop sign. They just stuck some small stickers to the stop sign, okay? But to the human eye, it will still look like a stop sign. But the autonomous driving, self-driving model, right? Autonomous driving machine learning model used in self-driving cars, right? It failed to recognize the stop sign. Ideally, in normal scenarios, it should have recognized the stop sign and it should have stopped. But in real world, it did not. It failed to what would I say? Classify that particular object as a stop sign, and it failed to interpret it actually. So this was a real-time experiment that was done by researchers long back. So these are the implications of model evasion attack. Like as I mentioned, very similar. We try to play with the input. To the human eye, it will look like very normal, but the model eventually gives incorrect results or misclassifies it. That is the idea behind model evasion actually.
Taking an example, you're saying like for a car, the model has been given 100 inputs. So it is like 101 or 102. That's why it is not able to identify.
Sorry, like on the adversarial sticker, right?
Sticker, right?
So basically, what would happen, right? We will try to play with the in case of images or objects, right? We try to play with the pixel values actually. So like when you are training a model or image classification, right? So models won't be able to perceive images or data as we humans perceive. Like model converts everything into numerical. Like it understands only numerical data, like zeros and ones, as we all know, right? So when we give an image of an object like a stop sign or a cat or a dog, right, it tries to identify patterns within that image, like the pixel values within that image. Like these set of pixel values denotes a dog. These set of pixel values, these kind of pixel values denote a stop sign. So it understands the data actually based on the pixel values, right? And it will try to classify that image or an object as either a stop sign or a dog or a cat or a human, right? So in this scenario, we made what they did was they changed, they would have changed some particular pixel values, right? But some particular pixel values. So the model would have caused a confusion in that machine learning model, whether to classify it as a stop, whether I should interpret it as a stop sign or I should interpret it as something, because it was not there in the training. It would not have gone through the training. So if it had identified the same pattern, it would have classified it as a stop sign. But now it has got a different pattern, which it hasn't learned before, or it is not robust. It hasn't learned before, or it is not robust enough to understand that pattern. So it failed to recognize that pattern. Eventually, it could result in accidents. So that's the idea. As I mentioned, these kind of model evasion attacks not only are like applicable to like self-driving cars. It could be like spam filters, malware detectors. The same attack can be applicable to all these scenarios, like sentiment classifiers, malware detectors, facial recognition systems. Okay. So here, like, there are two kinds of attacks. Like in model evasion, there are two kinds of attacks. One is like once we have the complete access to the model. Like in pen testing, we would say, right, like black box, white box, gray box, similar to concept, right? If we have complete access to the model, like we know everything about the model, we can query. In that scenario, we can query the gradients to understand, as I mentioned, right? From an attacker point of view, he wants to query the gradients to understand whether based on his input that he is giving, based on the input that I am giving, whether the model's loss function is increasing or decreasing. From attacker point of view, if I am changing the input, the model's output loss function should increase. Then only the model will misclassify it. Only if the loss function is increasing, the model will misclassify it. So if I have complete access to the model, right, I can make changes to the input and make sure the loss function is increasing and eventually deceiving the model, right? That is the idea behind open box attacks actually. Where I have complete access to the model, I can query the gradients to understand, like I'm making this small change to the input and the loss function is increasing. This is what I want, and I can eventually deceive the model. So this is done through some special algorithms like fast gradient sign method, Carlini-Wager. We will see about this actually. We will see about our Python package also. Like we don't have to implement all these algorithms from scratch for the attacks. We have a Python, like we already have an open source Python package called as Adversarial Robustness Toolbox, which implements all these algorithms: fast gradient sign method, Carlini-Wager, hop, skip, jump. So it implements all these algorithms, attacks. This is already available, where we can, like once we have imported that Python package, right, we can call all these algorithms using just a function. We don't have to implement all these algorithms from scratch actually. Now coming to the closed box attacks, now in this scenario we don't have complete access to the machine learning model, where we won't be able to query the gradients to understand like about the loss function. We don't have complete access, but in this case we have access to the confidence score I was talking about, the soft labels actually. Previously you would have seen about scores and soft labels, right? In this scenario we don't have complete access to the model. We have access only to the confidence scores, like how confident the model is in this particular category or in this particular class label actually. So based on the confidence scores that it has on a particular subject, right, like whether it's a picture of a dog or a cat, or whether it's a stop sign or a green signal, right, whether based on the confidence, right? So in this scenario the model only gives output as a confidence score, right? We will get only the final confidence score, and based on the confidence score there are again certain algorithms which we can use to attack the model and evade it actually. That is the idea behind this. This is the final one. This is the most real world scenario I would say, like most applicable to real world scenario I would say. So in this scenario we don't have access to the gradients to query the loss function, or we don't have access to the scores or confidence scores. We have access only to the final guess, whether it's a stop sign or a green light, right? Well, stop sign or a green light. We have access to the final output of the model, whether it's a cat or a dog. So in this scenario, we have access to only the final hard label. We cannot do anything with the model. So we hit a API, and the API calls the model, and the model gives the final output. So in this scenario, how we are going to evade the model? So that is also possible using a algorithm called as hop, skip, jump attack actually. So if you want to learn more about these algorithms, the research papers like have the complete implementation of how it is done actually. But from our point of view, from testing point of view, right? As I mentioned, we have a Python package like which is open source, which we can directly import in our code and then call all these algorithms with just using just a function, using just a Python function. We don't have to implement all these algorithms from scratch actually. But for our demo, we need to know about hop, skip, jump. As I mentioned, this is like a black box attack. Here we don't have access to the model. We have access only to the final answer of the model, right? So using it, will we be able to evade the model? So the idea how hop, skip, jump works, right? So it starts with an image which is already misclassified, right? It's already misclassified. So and then it makes some small changes to the images. As I mentioned, right, in case of images, we make small changes to the pixel values, right? And it queries the model again to give what classification is made by the model, right? So now we already start with the already misclassified model. Like we start with an entirely different image. Okay, and we make some small changes to the pixel values and again send it to the model to classify it. And based on the output it gives, it tries to estimate the boundary, the decision boundary I was talking about. So there are, say for example, there are two class levels. Let us, for understanding purpose, right, let us take a very simple example, cat or a dog, right? So it has to, like we will take a picture of a dog and eventually we want the machine learning model to classify it as a cat. Right, we take a picture of a dog and we want the model to classify it as a cat. Okay, so now like we are making small changes to the pixel values of the dog image and sending it, right, and see what the output of the model, whether it's a dog or a cat. Okay, based on the this happens again and again. Based on the classification result of the machine learning model, it makes some small changes to the pixel values again and again submits it to the machine learning model to get the output label. Okay, at a certain, then like using a binary search algorithm like we would have seen long back in data structures and all. So using binary search algorithm, it will try to approximate the decision boundary where the decision changes from dog to cat. So it will try to find, like it's like making a hard guess, right? So I'm making some changes, I'm sending it, and what is the output? The output is still a dog. I'm making some more changes and sending it. The output is still a dog. And I'm making some more changes and sending it, right? And finally, I would like I made the model to classify the image of a dog as a cat, right? So using this particular, like based on just the output of the machine learning model, right? And using binary search algorithm, we try to find the decision boundary where the classification changes. That imaginary line I was talking about, right? Where the classification changes from dog to cat, right? And the name comes from like hop, skip, jump, right? So it will try to stay around the decision boundary, make some changes, ask it to classify what is the output. It will try to stay around the decision boundary. So say if the algorithm has made some mistakes, right, it will skip that step. Like it made some changes and the output is the classification is not changing, it will skip that step. Okay, and again it will make some more changes, not the previous change, it will delete the previous change and make some more changes and see what our classification is, right? And based on like if the classification at some point like would change, right, it will try to approximate the decision boundary where the model classification changes, right? And with the small inputs, changes to the inputs, it has finally cast or evaded the model in giving incorrect results actually. That is the idea behind hop, skip, jump algorithm. We will see like the practical implementation. Sorry. There is one more thing called as L2 and L infinity similarity norms. We'll see about it in the demo actually. Okay, here for the demo we are using everyone able to see, right? Okay, for this demo we are using TensorFlow actually. So here I will highlight the code. We are using an already pre-trained ResNet 50 model actually. Okay, this is an already pre-trained model, right? We are not going to train a model here. This is already available in the internet. We are just going to load it through TensorFlow. This ResNet 50 model was trained on ImageNet, which is like ImageNet data set is kind of a, what I would say, It is a repository of multiple images, like millions of images with the classification. Like it has millions of images like cars, airplanes, animals and everything with the classification. So this particular ResNet 50 model is there on the internet. It's already trained on the ImageNet dataset. So it will be able to classify the images. Right? That is the idea behind it. We are just loading it actually. And as I mentioned, we are using Adversarial robustness toolbox. This is there for a long time actually. We are importing that package, and we are going to use hop skip jump attack. That's what we are importing first in the code. In this step, like this is not unnecessary, but before what I would say, really, we cannot take an image and give it as it is to the model. We have to do some processing and other stuff, right? Basically, what I would say, resizing the image. So that like the different machine learning models, right? They would have in their training stage, they would be able to recognize images that are of a particular size only. Like each model, it would be different based on the implementation that they have done, right? The ML engineer has done. Each model interprets images in a different way. So this ResNet, for this particular ResNet model, we have to resize the images so that we can feed it to the ResNet model for classification. So these are all the pre-processing steps that we need to do so that it understands the images and it can process the images. So as I mentioned, this is the implementation of the attack. Like here we are defining the, like we are loading the hop skip jump function, and we are defining the parameters actually. If you see like max eval, right, we are defining max eval is equal to 100. We are defining, we have to make only 100 queries. At most you have to make 100 queries to the model and causing it to misclassify. So see, the function should not run continuously, right, endlessly. It should not keep on running, trying to misclassify, right. So we are giving a norm saying like 100 queries you can make to cause it to misclassify. That is the top norm actually. So as I mentioned, since we have already imported adversarial robustness toolbox package in our code, right, so we can implement the hop skip jump attack algorithm. We don't have to define the algorithm from scratch. We can just import the function and use it with our code. We're just doing it. So it runs for like 15 iterations. Like here I would have mentioned the iteration. It runs for like 15 iterations, and it will try to make changes to the images and eventually causing the model to ResNet 50 model to misclassify it. Right? So here only we are generating the images that will be passed to the ResNet 50 model for misclassification. Okay, maybe I will run it, but I have already run it. But maybe I will show it. Maybe if needed, I will run it again actually. So as I mentioned, in this step only we are generating the images that will be used for our misclassification actually. So using hop skip jump algorithm, we are generating this particular step, right? Adversarial attack dot generate. Using the algorithm, hop skip jump algorithm, we are generating the adversarial images that will be passed to the ResNet 50 model for causing misclassification. Okay, and then like in the final, right, we are giving the generated adversarial images. We are giving the generated adversarial images and asking the ResNet model to classify it. So we are now generated the adversarial images and we are sending it to the ResNet model to classify it, whether it's a particular image or a different image actually, and we are printing the results. Okay, so I will show like for this particular thing, right, these are the images. We see here we have different stop signs. Okay, all are stop signs only. We have different stop signs, like real world example, right. On the left hand side, if you see, left hand side is the original prediction of the model. Like before we send the adversarial image, right, left hand side is the original prediction of the model. So we have taken 10 stop signs and we have given it to before we made some changes, right, we have given it to the ResNet 50 model and asked it to predict what is the class label of the particular image. So before we did the adversarial part, the original prediction is street sign only. If you see on the left hand side is the original prediction before we made some changes to the images. Left hand side everything is a street sign. The last one would be different. We see everything is there. So the model, initially the model classification is correct only. The model is working as expected, right? Okay. So as I mentioned, we implemented in this particular step, we implemented a hop skip jump algorithm and we created some adversarial images, and we asked the model to predict this particular step. On the adversarial images that was generated by hop skip jump function, right? We asked the we generated 10 adversarial images and asked the model to predict whether it's a stop sign or something. Like it depends upon the model, right? On the right hand side is the adversarial image, right? Right hand side is the adversarial image, and if you see, the classification has changed. Okay, so here if you see, to a human eye, it is still a stop sign only. To a human eye, it is still a stop sign. But the model, like if you look closely, there would be some noise added to the image. The the red, blue, green pattern, there will be some noise added to the image. But the original image is this one. There is no noise in it actually. But in the adversarial image, there is some noise added to it. These are like RBG, like RGB, sorry, red, green, blue image noise, right? That we are adding to the image. And eventually, the model, to the human eye, it's still a stop sign. Nothing has changed. But the model misclassified it as a soccer ball. This is the output, the prediction from the model, soccer ball. And it changes actually. If you see the second image, it classifies it as a parking meter. Again, soccer ball. If you see this particular scenario, right? This particular scenario, basically I would mention, like we ran only 15 iteration of the hop skip jump attack. Like we can increase the value also, but it will keep on, the time will be more. It will keep on running, right? So in this particular image, it was not able to find any patterns that it could modify. The algorithm, right? Hop skip jump algorithm was not able to find anything that it could modify, and eventually caused misclassification based on the parameters we defined, right? Within the stipulated time, it was not able to find a pattern to cause the machine learning model to misclassify. That's the reason if you see that it is very similar to the original image, and the prediction is also street sign only. So the model, the hop skip jump was not able to evade it in this scenario, in this particular scenario. Spatula, rubber eraser. So these are the predictions. And that is one thing I wanted to mention was like the L2 distance. This again is a mathematical function which is used to denote how similar the adversarial image is to the original image. Ideally, the L2 distance should be like very small. L2 distance should be very small. Then only we can say like this adversarial image is very similar to the original image. Okay, but in this scenario, if you see the L2 distance is 300, 300 is okay, fine. Like the adversarial image is like very similar to the original image. But if you see this and all, L2 distance of 4532, the adversarial image is not very similar to the original image. Like we can see the noise clearly. That pattern, right, RGB pattern, right, we can see the noise clearly. Ideally, in a real world scenario, we don't want this much long L2 distance. But for a simple demo, this is acceptable. But in a real world environment, if you want to bypass the model, right, the L2 distance should be small. Like in case of 2 digits or 3 digits, then the adversarial image like very similar to the look. It will look very similar to the original image, but the model will misclassify it. That is the idea behind it. Okay. I will run it, and if you run it again and again, right, the output, the adversarial image output, the classification also will change. Here we are executing the attack. It will take some time, as I mentioned, 15 iterations. During this process, it will try refining the image to cause the misclassification. Okay, now this is done. Now the adversarial images have been generated. We give it to the ResNet 50 model. We give the original images as well as the adversarial images that were generated by hop skip jump attack, and we ask it to classify it. Let's see if there is something is changing. I think the number, sometimes the prediction also, sometimes the L2 distance also will change actually. If you see, the L2 distance has increased from 4000 to 5000 actually, and the classification is still the same actually. This classification is still the same. Okay. Any questions until this part? Like this is only for a image-based classification model. Any questions until this part?
How do we fix this attack?
We train it actually. We during there is a concept called as adversarial training actually. So in this case we are trained with the ResNet 50 model, right? Got trained on ImageNet data. So during the training phase itself, we execute this attack during the training phase itself, so that it becomes more robust to it. Or there are another concept called as ensembling actually, where we take the output of one model and give it to another model. So in this case, top skip jump algorithm was able to bypass one model, but at the same time it won't be able to bypass two different models. So we take the output of one model and give it to another model. So top skip jump cannot bypass both the models at the same time, right? At a certain frame of time. So the idea is that is called as ensemble modeling. That is one way, and the most proven way is like using this adversarial attacks in the training phase itself, where we to do the training for ResNet 50, right? So that it becomes more robust to these kind of attacks actually. I don't know a universal solution to it. From what I studied, these were the two proven methods like I saw in various research papers actually. Any questions? Okay. Yeah. We move on to the next one actually. Here for this demo, I will explain what we are going to do actually. We are going to take a data set. I'll show the data set itself so that it is more easy to understand. So we have a CSV file with two different columns. One is the query and another one is the label. So in this scenario, we have normal SQL queries to retrieve data from the database, and we have the SQL injection queries also, the malicious SQL injection queries also. So we have the normal queries and as well as the malicious SQL injection queries. So we have the label. Label 1 denotes that it is a malicious query, right? Label 1. Label 0 denotes that it is a benign query, like a normal query, normal SQL query. Okay. So we have this very simple data set that was taken from Kaggle actually. So we have malicious queries as well as normal SQL queries. This is our data set using which we are going to train a machine learning model to identify SQL injection attacks. Like whenever this these kind of malicious queries would come, right, the model has to classify it as malicious. And if anyone gives a normal SQL query, the model has to classify it as benign, normal. So we have the labels on the right side also, zeros and ones. We have the normal queries. Something else. Yeah, this one, normal queries. And the malicious queries. So we have 30,000 queries in total actually. It is not coming here actually, but we have 30,000 queries, which includes both normal queries as well as SQL injection queries, and we are going to train a model to classify whether the query is normal or malicious. This is the data set we are going to use actually. And then once we have trained the model to classify whether a SQL query is like a normal query or a malicious query, then we are going to attack the model using another model. We are going to use another machine learning model to attack this trained machine learning model to eventually causing it to misclassify actually. So we are going to give generate a malicious query and we are going to submit it to the trained machine learning model, but the trained machine learning model will classify it as a normal SQL query. So it basically bypass, like SQL injection bypass. So that is the idea behind it. Before that, we need to understand these concepts actually. So if you are going to submit SQL queries as it is to the machine learning model, it's not going to understand. Like it doesn't have the capability to understand what is an SQL query, what are the intrinsics of it, what are the features associated with an SQL query, right? Anything, if you want to train a model, right, anything, text, image or video, anything, right, we cannot give it as it is to the machine learning model. Okay, so we have to, there is a process called as embedding, where we convert the video, audio or text sample, right? If we need to train a machine learning model or we need to give this data as input to the machine learning model, we have to convert it to a way that the machine learning model can understand, right? It doesn't understand images, it doesn't understand text or anything. So we have to convert it into numerical values actually, right? Only the machine learning models in the field of machine learning, right, they understand only numerical data. So here these are small concepts that we need to understand before we can go to the demo actually. There are different, here we are talking about vectors. There are different concepts like vector is, I would say, is like a list of numerical values that denotes a particular text, image or video. If I explain orally, it won't be easy to understand, but I will show the actual vector how it looks. Okay, this is the numerical list of values. This particular, say there are 3 values here, right? The first one is an SQL query, the second one is also an SQL query, third one is also an SQL query. But as I mentioned, machine learning models, they are not going to understand SQL queries. So we convert into a format that they could understand, which is a vector here actually. There are other concepts also like NumPy arrays or tensors, for example. So vectors are like a single dimensional array of numerical values. This is like single dimension array of numerical values. Like as I mentioned, right, for us, we can understand like how the SQL syntax will look like, how it works and all. But in order to make the machine learning model understand the SQL query language, right, we have to convert it to a format it could understand. This is the format, the first one highlighted, right? This is a single SQL query. That is a single SQL query. But this is how the model interprets in the backend actually. This is a vector. This is how, like a simple explanation of vector. So here if you see like this particular vector, right, there will be like 100 values, numerical values. These 100 numerical values will explain, like these are the features of that SQL query. Like it interprets the SQL query in a way it could understand. These are the features of that SQL query actually. It extracts like select star from table or something, right? It extracts some relationship between the different words in that SQL query, and this is how it has represented it in its backend actually. Okay? This is how it has interpreted an SQL query in its backend. To explain features in more, I will show one more example so that you can understand what is a feature. Here there are, for that particular single SQL query, right, there are 100 features. So it is taking 100 features to represent a single query, SQL query, right? I will show another example to explain what is a feature. Okay, there is an EDR called Endgame actually, EDR, that now acquired by Elastic. So it is called as Elastic EDR or something. Okay, so what that Endgame they did, right? As I mentioned, they like in the beginning of the demo, right? I mentioned to train a machine learning model on classifying malware, right? You take malicious samples and you train the machine learning model in order to in order to understand the different patterns that the malware uses, right? So what this Endgame EDR team, right, they did, right? They collected thousands of malicious samples. They took different features from that malicious samples, like malicious executables, right? EXEs or any malicious executable, right? They took all the thousands of, like millions of malicious executables, known malicious executable. They extracted features from it. When I say features, for example, the first one, byte histogram or byte histogram entropy. Maybe I will explain something which is easy to understand. The functions that executable imports, the functions that particular executable imports, right, are metadata of that executable.
Any specific questions from anyone can ask now. Okay, I have a question. Okay, for example, as you have taken into the ML model state, let's assume there is an ABC company have developed some models, and if you want to find vulnerabilities, what would be a strategy?
It depends upon the implementation, right? What is that model, what they are doing, where the input is coming from. Like as I mentioned, right, there is predictive AI and generative AI. What exactly the model is doing and what would be the input? The input would come from directly from users like a chatbot or something, or it scraps the internet and takes input from some random places. Then I can put some random data or malicious data in a web page like Wikipedia, and if the bot is scrapping Wikipedia, it could pull in the data and I can use it to exploit some data or cause the model to misbehave or give incorrect results.
Okay.
It depends.
Let me give an example. So it is a chatbot, and let's assume they are using that particular chatbot or kind of an application within the company. Okay, so for example, to automate a certain activity. Okay, so they are using Claude chatbot. Okay, so Anthropic, that particular companies. So in that case, like you have a chatbot and you made sure like for application security you did some kind of automation. And what are the various vulnerabilities and how level do you think it can happen?
This is like more like the thing we have learned about is like prompt injection, direct and indirect prompt injection. But you mentioned Claude, right? Claude would have already gone through multiple this kind of adversarial training and all. Unless or until a new jailbreak or something comes up in the Claude model, we cannot do much with Claude model, right? Otherwise, like if we have developed our own in-house model, that is easy to break the jailbreaks or like it basically we can convince the model to give more information than what it is supposed to give. But in terms of Claude and all, I think it would, like I haven't done much like to answer your specific query, right? Like I haven't done much related to, like for example, attacking GPT or like OO3 Mini or Claude and all, right? So I don't have a complete answer. But unless or until a known jailbreak or something comes up, right, it is difficult to bypass these models to give some additional data actually. But in-house developed model, the basic attack still applies. Prompt injection, like excessive access, like you would have seen about the OAuth stop then for LLMs and all, right? It is giving something which is not supposed to give actually, some sensitive data, right? Or it should not reveal the system prompt or something like that. And also there are other attacks also, like the excesses and all. Like say for example, you're taking in the input and you're sending it back to the UA, right? You're sending it back to the UA. The excesses and other things and all. Or say for example, if we based on the training it has undergone, right? One user is asking one question. Okay, I submit some comment. And in the comment, I give some XSS JavaScript or HTML code or something, right? Say for example, that machine learning model has learned from it. Okay, and it uses my comment or the comment from Jira or Confluence or some public forum, right? And if it has read that comment and uses it to give provide an answer to some other user. Now it has taken the answer from me and it is using my answer to submit to another user who has asked a query. Then there is possibility about that XSS and other things and all.
Okay.
Or exfiltrating data.
You have 5 to 8 more minutes.
Okay. Then I will think I can conclude with model evasion. I don't think we can go to model poisoning. Okay. Yeah. Like I will quickly summarize. Like I mentioned about features, vectors, and all, right? So we take a malicious sample. Okay. That malicious sample will have a hash signature. Like very common is a hash signature, right? And it would be importing some functions. Or exporting some functions that would be like, or importing some functions. It would have some metadata. It would have some hard-coded strings, like the domain names it should contact, URLs it should contact. So what they did, right, the end game, they took thousands of malicious samples, and they extracted all the features from the malicious sample. One I would say like entropy, byte entropy, the very first column you see, right? Entropy. Entropy determines the randomness in that executable. Say for example, if the entropy is high, right, that means they have encrypted that executable. When do we normally encrypt executables? Like if we try to encrypt the shell code, right? If we want to obfuscate something, we do encoding or encryption, right? If we want to obfuscate, we try to stay under the radar. We don't want them to decrypt it, right? Then we do the obfuscation, or in case of malicious samples, right? If you are into malware development and I want to develop malware, then I want to encrypt the shell code so that they don't get to look into my shell code, right? So whenever we are doing some kind of obfuscation or encryption, right, the byte entropy will change, the entropy will increase. So they have taken, as I mentioned, they have taken thousands of malicious samples. They took the entropy level of each of the malicious sample and converted into numerical vectors. These are the numerical vectors. So they took all the features from the malicious malicious malware samples. One is byte entropy. If you see, you would have heard about like whenever you have an executable, right, you have to, it would be importing some functions or exporting some functions to be called by other binaries. The header info, the executable header info. There are multiple things. The strings, the hard-coded strings I was talking about, symbols. So they extracted all these data features from the malicious samples. Okay, and this first row, right? The row is a single vector. I mentioned a one-dimensional vector. So this denotes, the first row denotes a single malicious sample. The second row denotes another malicious sample. Third row another malicious executable. So these the features, we can call it as features or dimensions. It differs actually. These are all features. Here we have 20 features. So this 20 features denotes one particular malware, one executable, right? So we are using this for each malware. There are 20 features. For each malware, there are 20 features, and we are taking this data and we are training the machine learning model. Eventually, like if it trains on this data, right, if it sees the same pattern, same strings repeated in that executable, same file header, or same imports and exports, or same entropy level, right, the model will think this is something malicious. The model will think this is something malicious. That is the idea behind it actually. So the reason I showed this was like to understand what is a feature, right? We can, as I mentioned, we cannot take the malware and submit it to a machine learning model to say, like, to classify it as malware or not. We need to submit in a way it can understand. So we need to extract that features from the executable and we need to give it in a format that the malware, the machine learning model can understand. This is how it is done. Okay. So as I mentioned, in that scenario, in the malware scenario, that was a synthetic data, not an original data, but we have the data set in GitHub actually. That was done by Endgame actually. That particular malware sample had 20 features. So that denotes a particular malware. Here, this particular SQL query has 100 features. This is like 100 values or dimensions. So this denotes a single SQL query. The second one, another SQL query. This is another SQL query. So this is how it interprets an SQL query for it to understand actually. Okay, I'll quickly run through it. So as I mentioned, vector, whatever we saw there, right? Vector is like kind of a numerical data to denote text or image in a way the machine learning model can understand. So how we could convert text, image or video into vectors, that is done through a process called as embedding. So the embedding is the process like method we use to convert data, images, video or text into vectors so that the model could understand. And in our demo, we are going to use fast-tag embedding, which is specifically for embedding word, text data, text-based data. Like we have different embedding, embedding package, embedding algorithms or models for a different data set. For image, that would be a different model. For video, that would be a different model. In our case, since it is an SQL injection query, we are going to use fast-tag embedding. So it converts the SQL query into a format that the machine learning model can understand, the vectors that I was talking about. And the reason behind embedding is, right, as I mentioned, machine learning model won't understand the intrinsics of an SQL query. It doesn't understand what is like select, insert or different statement, right? So the embedding is to the embedding is to let the model know the semantic meaning of an SQL query. So it cannot say for example, for evading a machine learning model, right? We cannot say we remove select statement, we put some garbage statement, right? We put something that doesn't make sense, and we say like it has evaded the machine learning model. The SQL query should work. The SQL injection query should work. It should be malicious, but the model should misclassify it. But for the SQL injection query to work, the machine learning model should understand the flow of the SQL query, how the SQL query is structured, right? So instead of a select statement, you should not put an insert statement. Somewhere randomly, you should not put the insert statement and say I have bypassed, right? So it should understand the complete SQL query language. That is done through embedding, so that it understands the semantic meaning of a particular SQL query. Like vectors, you would have seen, right? There were like 100 features, right? For this particular demo, 100 features. Okay.
Or you can skip to the demo.
Okay.
We have got an idea about the demo. We don't have got an idea about anybody.
Okay.
It's more detailed, right? Probably you can.
Okay. As I mentioned, right? Like we take that SQL injection CSV file. We have the query and the labels. We are using fast embedding so that it gets converted into vectors I was talking about, and the 100-dimensional vectors actually. So this is to let the model know how to interpret the SQL query. Okay. Then there is something called as the variational autoencoder. So I mentioned, right, that vectors have 100 dimensions, but we can still compress that 100 dimension into 32 dimensions so that it is easier for the model to learn. The model doesn't have to learn all the 100 features. It can learn 32 features and then still interpret a query as malicious or benign, right? So that is done through this variational autoencoder. Here we explicitly define, if you see latent dimension is equal to 32.
So this is basically for training the model, right?
Yeah, exactly.
You can skip to the part where you are trying to do, or you are going to.
Yeah, okay. Yeah, then once you convert that, right, we are training.
Assume that we are getting into an adversarial attack on model, so it's not deep into training of the model.
Okay.
Same time, that's it.
Okay.
It's very interesting. I will listen whole day, but.
Yeah, understand. Like only like I'm just saying, like I'm going to classify train this particular model, XGBoost model for classification. And in the initial training, it is able to classify a benign query as benign, a malicious query as benign, malicious. For example, 0 is benign, and 99% of the time it is able to classify it as a normal query. The 1 is malicious. 100% of the time it is able to categorize the query as malicious. Okay, now we are going to train another, as I mentioned, right, there is a concept called generative adversarial network, GAN actually. So we are going to train the model. Previously we would have seen the variational autoencoder output, right? We are using the output of variational autoencoder, we train the XGBoost model. Okay, using the output of variational encoder, we train the XGBoost model. We use the same output to train another model. We train another model, but this model, what it does, right, like I have to explain this particular slide. Only one slide. Okay. So what it does, right? The generative adversarial network. There are two particular concepts: generator and critic. What happens, right? The generator generates synthetic data, something which doesn't exist. It generates synthetic
noise.
Yeah, noise. Yeah, it starts with noise.
And it improvises to find whether it's real or not.
Ultimately.
This is the base for any generative AI, right?
Exactly.
This is the base for generative.
Exactly. So generative, this can be used for training also or adversarial attacks also. As I mentioned, to answer this question, right, in the training phase, we can use GAN to generate adversarial data and use it for training also. But in this scenario, we are going to use it for attack actually. So we have the generator which generate fake samples, and the critic, right, they play a game. Where they generate fake sample, and the critic, where the job of a critic is to classify whether it's a fake data or original data. It has to classify whether it's fake or not. So until one point of time, if we do this training again and again, right, at one point of time, generator will generate some fake samples which the critic won't be able to misclassify, like differentiate between an original query or a malicious, between a original data or fake data. So that at one point of time, critic won't be able to differentiate the fake sample from the original sample, the original data set that we used, right, SQL injection. So both will be very similar. Okay, so we are going to train it and use it to attack the XGBoost model that we trained. Okay, so we are going to train the generative adversarial network based on the data we have, and at one point of time it will be able to generate fake data. It can generate malicious queries also, it can generate benign queries also, but at one point of time during the training phase it will get more robust, that it can generate synthetic queries which can eventually bypass a SQL injection detection machine learning model. It undergoes, like, it runs on its own and it will be able to generate queries which can be used for bypass. That is the concept. So ultimately the generator generate fake data, and we use the fake data that the generator generated to attack the XGMooves model that we trained in the first step. In the first step, we trained a model to classify SQL injection queries, right? So we use this output of
data. You are using the same data for generative adversarial network
for training it.
Synthetic data.
And using the synthetic data,
Which can be many. So what's the output of the generative adversarial network?
it can generate fake data. That is the idea.
Synthetic data. Are you focusing on?
It can generate both. It can generate both benign and malicious.
Okay.
It will learns on its own. It can generate both. This particular implementation called as a CWGen-BGP. No. It's more like conditional. We generally explicitly give labels saying this is a malicious query, this is a benign query. You learn on its own and you generate synthetic data. And we use the synthetic data, which is the output of the GAN, to attack the XGBoost model. And this is the output.
So it can have both valid data and invalid data.
Exactly. So the Jan generated 500 SQL queries, okay, and that getting like 500 malicious SQL queries, and the XGBoost model that was trained in the first step, right, misclassified 321 queries as normal queries, but all are malicious only, but the model misclassified the SQL injection queries as normal, okay, 179 queries it identified as malicious, which is the right answer. So it had 60. It differs actually. It differs. This is a very simple demo, but in case of real world environment, they will do the training again and again and millions of times. Like, it will go on forever. This is a very simple demo, like, which happens like 1 minute actually.
So in this case, you have used generative adversarial network to generate only malicious data.
Yes, I mean it can generate benign and malicious data, but for the demo I used malicious synthetic data. So it trains itself to generate malicious queries on its own, synthetic data. So that's it. Like, maybe we'll see about model poisoning some other time.